Good evening again. I'm going to start on this slide. My daughter was in the room and she's trying to do sign language with me and I'm trying to talk and then I got all mixed up. So I apologize for that. So the fundamental characteristics of an ideal gas. So we are talking about PVNR, PV equals nRT. We do not care about the volume of the individual gases. We do not care about the force of the individual gases either. If we worried about those, then these factors would be important because pressure would be exerted, and so it would be a function of the individual particles. And then we would have to take a look at a temperature again and the volume of the container, which we will see here at the end when we start talking about van der Waals forces. And so PV equals nRT is not taking any these into considerations. Now, the other thing that you want you to think about here in a little bit, that if you think about, I have a container of water that is going to be boiling. Okay, so these gas molecules are moving very, very fast, very, very fast. And when they gain enough energy, gain enough kinetic energy, they want to bust out of this situation and they want to become a gas. Now, gases are going to be the least ideal. They're not going to behave ideally right at the boiling point. Now, if you think about that, you have all these interactions. You have some molecules that are losing energy and they're going to go back into the liquid phase, and you have some that are gaining energy that are coming out. There's tons of interference right here. Because of that interference, gas molecules do not behave ideally at the boiling point or right above the boiling point. Okay, so this leads us into mole fraction, which we're going to talk about here. Mole fraction is the ratio of the number of moles to the total number of moles in a mixture. Mole fraction is going to be shown by the Greek letter chi, so this is CHI, is equal to the individual mole, mole 1, mole 2, how many ever moles we have, over the total number of moles in our system or in our mixture. And if we go ahead and keep applying Dalton's law of partial pressure here, we can continue to compare this and say that pressure 1 is equal to the total pressure, which we already know, which is a ratio. So we can do any kind of combination of this, and you're going to see Dalton's law of partial pressure in a variety of ways. One way that you're going to see it is if you solve for pressure 1. So let's say we want to find the pressure of an individual gas in a mixture, which would make sense to you. So let's say we wanted to find the pressure of nitrogen gas in the gas that you are breathing in right now. We would say that it's going to be equal to the mole fraction of that mixture times the total pressure. So you can see I just simply solved for P1, cross multiplied the ratio of chi over or times the total pressure. So this is Dalton laws of partial pressure, just looking a little fancier than what we've seen it before. So this is very similar to what we did with the butane lighter. We did not heat our butane. That's why it was a little bit easier to collect the gas. But again, we are talking about the production of oxygen by thermal decomposition of potassium chlorate. And in this situation, sorry, hold on, another little interruption. Okay, problem averted. So we are collecting this water over a gas again, which is some principles that we need to take into account. So here we are talking about a wet gas because we are collecting it over water, which is what we did with our butane lighters. And so we know that there's going to be a vapor pressure of water that is going to be present. And this vapor pressure is going to create a pressure, and so if you think about what we were doing is that those water molecules are escaping from the surface of the liquid. So they're evaporating and they are going to collect on the space. They also are collecting in the space that you are collecting the gas. And so what is going to happen here is you're going to have a vapor pressure of the water along with the pressure of the gas that you are collecting. Now it's going to be temperature dependent because if there's a higher temperature, the molecules are going to move faster and you're going to create more pressure within the walls of the container. So then that leads us to the kinetic molecular theory of gases, which I already mentioned a little bit earlier. But the volume of the particles can be assumed to be zero. We are not taking into consideration because they're very, very small. There's great distance between the molecules. We're hoping that there isn't any interaction, and so we can talk about PVNR then. The particles are in constant motion. The collision of the particles with the walls of the container cause some pressure. That should make sense to you. So if I have a wall of a container, I have a gas particle, it's going to collide, it's going to create some pressure there. Now, depending upon this speed is going to depend upon the amount of pressure that's there. Particles exert no forces on each other. So what this means is if I were to interject another particle into here, another gas particle, that there is no forces in between the two. And then the average kinetic energy, remember this is movement, is assumed to be proportional to the Kelvin temperature of the gas. So we are talking about that if I increase my kinetic energy, all right, the movement of the gases, I am increasing my temperature. Well, that should make sense to you because temperature is really a representation of how fast the molecules are moving in a system. So real gases, do they exert forces? Absolutely. But again, we are studying this, so there's no interactions that we can make this a little bit easier for us to understand. So if we take a look here, they have, they're looking at the ratio of the volume of gas, gaseous nitrogen, so we have gaseous nitrogen, we have liquid nitrogen. If we do the math and the spacing of the molecules is 9 times farther apart in the gas than they are in the solid. And so you can see here again, 1 mole of any gas is 22.4 liters, which upholds Avogadro's law. So in general, we can say that in the liquid form versus its gaseous form, gases are approximately 1/10 the density of the same material in the liquid phase. Approximately 1/10. All right, so now what we're going to be doing in these last few slides is we're going to be using our kinetic molecular theory and the ideal gas law to predict what's going on here. So we have increased pressure due to decreased volume. Well, we got pressure and we have volume. You should recognize that that is going to be Boyle's law. So if we have a decrease in volume means that I better have greater collisions going on to create this greater pressure. So how are we going to do that? We are going to decrease our volume. Again, we are looking at Boyle's law, so we are saying that we are increasing our pressure, so the volume better decrease, and we are holding constants of the number of moles and the temperature in this situation. Okay, if we go ahead and look here, we have increased pressure due to increased temperature. So here we are assuming that our K constant is going to be volume, so we're holding our volume constant. And if we take a look at increased pressure due to increased temperature, so we are saying that our pressure is proportional to our temperature. And so this has to do with the speed of the molecules. The speed of the molecules are going to increase with increased temperature, creating more collisions, creating more pressure, and I'm keeping my volume constant. So if I want to increase my pressure and I'm not changing the amount of volume, it should make sense to you that I have to have more and more collisions so that I can increase that pressure. How am I going to do that? Increase the temperature. Okay, here we have the effects of increasing the temperature of a sample of gas at constant pressure. So you can see these two weights that I have sitting here is signifying that I have the same pressure on my system. And so this is going to be Charles' law. If in order for this to be true, I have to increase my temperature and I need to increase my volume if I'm going to keep my pressure constant. In order to do that, I got to heat this gas. When I heat the gas, what happens to the kinetic energy? Hopefully you're saying it increases. Then what happens to the amount of pressure on the walls? Well, they're going to hit the walls. The gas molecules are going to hit the walls with more force. And in order to keep that pressure constant, I have to increase the volume. So this is Charles' law. And the last one is we're going to increase the volume due to increased moles of gas. So we're taking Avogadro's law here. So you can take a look here that we have the constant temperature and pressure, constant pressure right here by our one little weight that's sitting here in our diagram. And so we are increasing the number of moles. So you can see the gas cylinder that they have here. So we have the same temperature, but I have increased the number of gas molecules. What's going to happen? Well, I'm going to have to increase my volume if I want the pressure to remain constant and to be the same it was in its original state. So hopefully this is Avogadro's law by putting in more moles of a gas. Hopefully you can picture this, you guys. If you think about this, I'm adding more moles. There's going to cause more pressure because there's going to be more collisions. And so if I want to maintain that, I'm going to have to increase the space in which those collisions are taking place. All right, that leads us to root mean square velocity, which is going to be something new. And so we're going to tackle that next. Have a wonderful night.